So we just talked about temperature sensors that convert temperature to a resistance change. The next time of resistive sensor we're going to discuss are strain sensors. And these are sensors that convert a strain, that means an elongation or a deformation, into a resistive signal. And we're going to discuss two types of strain sensors. First, the piezoresistive strain gauges, and then the metallic strain gauges. Strain gauges. So strain gauges are sensors that convert a strain or an elongation to a resistance change. Let's see what happens if you strain a material in general. We're seeing that on this side here. So this is just a cylindrical rod with length L, diameter D, and a cross-sectional area A, and a resistivity. Resistivity is a material parameter, ρ. And if I'm going to strain that material, I'm going to elongate it, so L becomes L plus delta L. I will see that I'll get a change in resistivity and or a change in diameter here. And if we also look what is the resistance of such a structure, well, the resistance equals the resistivity of the material times the length divided by the diameter A here. And so if we want to know what is the sensitivity of the system, sensitivity here is defined, or in general is defined as the relative change of sensor output, so relative change of resistance, divided by the relative change of the physical property that I want to measure. So that's the relative change in length. So that is the relative resistance change divided by the strain, and that is the sensitivity. And this factor here is called the gauge factor, G, and it's by definition looking like that. So let's see, what is this delta R over R? Well, we know what R looks like here, and then it's just pure mathematics. If you do dr over R, you can equals delta rho over rho plus delta L over L minus delta A over A, because it's a division here. And so we also know that delta A over A, so the area A is relative to D squared, so dA equals 2 times dd, and so you can easily find this formula. And so we have a general formula for then the gauge factor, the resistivity. And now if we work that out, you see delta R over R, so you get this one divided by this one, equals actually the delta, this term, delta rho over rho divided by this one, plus delta L over L divided by delta L over L, it gives you 1, minus 2 times delta D over D over dL over L. And we can further simplify that by noticing that this factor here, the change of diameter of the rod versus the change of length, that is what we call a Poisson ratio. And if you work in material science, you should actually, as an engineer, you should know what a Poisson ratio is. What is a Poisson ratio? Well, Poisson ratio is if I have a cube of material, say 1 square meter cube of material, and I'm going to compress that from the top to the bottom. Say, for example, it's 1 meter in cube, and I compress it 1 millimeter. What's going to happen if you compress the material is going to expand on the sides, because the material that you compress will have to move to the outside. Basically, yeah. And then the question, the rate, I mean, the expansion on the side versus the compression ratio, that's called the Poisson ratio. And for any material, the Poisson ratio will typically be in the order between 0.2 and 0.4, but typically 0.3. That means if I compress 1 millimeter in this side, it will actually expand 0.3 millimeter in that side. So this is a fundamental material parameter, and it's actually expressed here as written here as dd, the relative change in diameter versus the relative change in length. So I know that this is always 0.3, so it's almost constant. So I get 1 plus 2 times 0.3 is roughly 1.6. So I have a general formula now for my gauge factor, which is the gauge factor is the relative resistivity change plus a constant factor. And now we're going to see there's two types of strain gauges. We have the metallic ones and piezoresistive ones. Let's first have a look at the metallic ones. Metallic strain gauges are just basically Typically they look like this. They look like a little plaster, a little piece of tape, typically like 2 centimeter by 1 centimeter in size. And on that tape there's a little tiny wire printed and with 2 ports. And if this thing is now glued on something and that thing is expanding, what's happening is that each of the small wires will expand, so they will get longer and thinner, and therefore the resistance will go higher. Very simple principle. And now let's look again at our strain gauge that we just looked at, the gauge factor. So we have this factor, the resistivity change plus a constant. But we see that if we pull a metal out, if we expand a metal, the resistivity of the metal itself does not change. That's a material parameter. And it's not because I pull my metal, I deform it, that I get a different, resistivity or conductance of the material itself. Sure, the geometry changes, and that's this factor 1.6 here, but this change here, that will be 0. So therefore I know that for any metallic strain gauge, the gauge factor will be always around 1.6. No matter what metal I use, it will always be more or less the same. The second type of strain gauge is a piezoresistive one. And here, of course, we do the same type of elongation, but here something happens. If I have a piezoresistor, of course I have my same gauge factor here. Now I see that actually a piezoresistor, or a semiconductor material, if I'm going to elongate that, my resistivity rho is not going to be constant anymore. Yeah? How does that come? Well, I have a band structure, and in the unstrained state, so in the original state, I have a certain energy gap, and I'll have a certain likelihood for electrons to jump here. Of course, it's going to be temperature sensitive. But at a fixed temperature, I'm going to have a certain chance of electrons jumping, or minority carriers jumping from the valence band to the conductance band and creating conductivity. If I strain the material, I change the crystallographic structure of the material, which means that my band structure is going to change. It's going to become more difficult for so the energy bands are going to become higher, and it's going to become more difficult for an electron to jump from this point to this point. So I see my entire resistivity, delta rho, will change. And it will do that to an extent that delta rho over rho plus delta L over L, this change here is typically in the magnitude order 100 to 200. And then I see I have if this is 100 and I have plus this 1 plus 1.6, this becomes totally, negligible compared to this factor that's like a 100 or 200. So we can forget about this one. So we get the gauge factor is basically just this term that's left. So far, gauge factor. So we saw that we can use resistors to measure temperature. We can use resistors to measure strain. Now we're going to see how we can use resistor to measure a magnetic field using the Hall effect. This is a schematic of Hall effect sensors. In a Hall effect sensor, you send a current from one point to another here, point 1 to point 2, and you measure the voltage over these two, or between point 3 and point 4. Now, if I have a magnetic field that is out of plane, it comes in this direction, my electrons that come, they are moving carriers in the magnetic field, so they'll be forced to turn in one direction or the other. So we'll see that the density of the electrons will shift, so you get there will be higher electron density on one side than on the other side. And that is something you can measure by measuring the voltage drop here. So the magnetic field will change where the electrons run into material, the minority carriers, and that is something I can pick up over these two terminals. That will form my magnetic sensor. To finalize the potential principles, I'm going to stop with a quiz question. And which of the below statements are true? There can be none or all or one or two of them can be true. The first statement is, the resistance of a metallic strain gauge changes rather linearly with a strain. The second question is, the resistance of a piezoresistor changes rather linearly with a strain. And the third is, piezoresistors can be used as thermal sensors. So which of these are true and which are not true. Well, let's look at the answers. The resistance of a metallic strain gauge changes rather linearly with the strain. Yes, we've seen that. We've seen the resistivity. The gauge factor is about 1.6. It's a constant. So we'll have that will be rather linear change. The second, for a piezo resistor, is that still true? Yes, it is still true, because here's also here the gauge factor is typically 100 to 200. So it will still be constant. I mean, there's no difference between these 2 points, and still it will be a rather linear change. And the third one is, piezoresistors can be used as thermal sensors. The answer on this one is yes, they can. They are actually made typically for measuring strain, but they will also be temperature dependent. And you can see that in the principle, of course. You have the electrons jumping from the valence band to the conductance band. And that is dependent on the temperature. So even though you make such a sensor to be a strain sensor, it will of course strongly depend on the temperature also, which can be problematic. Because now you're going to have the situation that you try to measure a change, but actually you're measuring a temperature difference. So you'll have to be very careful that your measurement happens in always a constant temperature. If that is not possible, you'll have to do something to temperature compensate that. And that is something we're going to talk about in the next part, which is the bridge coupling, whetstone bridges. So for example, here I have, for example, a strain sensor, Rx, coupled in a scheme that looks like that. You have 4 resistors, and I'm going to put a constant voltage over here and measure the output here. How that exactly works, I'm going to show, or why this works as it does, I'm going to show in the next video. What I just want to explain here is that this type of scheme can be used to make a measurement temperature insensitive. If I put a strain gauge here and a strain gauge here on both these sensors, and they're the same, then I know, of course, my voltage drop will be, the voltage I get here will be exactly E over 2. It will be the half of this voltage drop. Yeah? So, and if they are both exposed to the same temperature, then of course heating up the structure will both increase this resistor and this resistor. But if they both increase, if they both increase at the same rate, still this point remains in the middle. Yeah? So this system becomes temperature insensitive. And what I can do now is that I can put this strain gauge onto my elongating beam that I want to measure, on the structure I want to measure the strain in. And this one I put next to this one, but not very close to it, but not on the deforming structure. So this strain gauge is a strain gauge, but is fixed on a solid piece of material that cannot deform. So I know that there's no deformation here. So any deformation due to strain will only affect this one, but both will be affected by temperature change. So this system will make that this voltage here will be only dependent on the strain and not on the temperature. Now in the next video I'm going to show, you should also look into these formulas and you can derive them yourself. You're actually supposed to have learned that in your electrical measurement technology courses. But you can try to do that yourself. These are kind of bridge couplings you're going to use in your measurement lab. And in the next video I'm going to explain exactly why a bridge coupling looks as it does. And I'm going to explain that for this sample, and it's up to you to try to figure it out how this works for a full bridge.